Okay, so I want to do problem number 34 and 20.2 because water seems fun. So they give me a vector field, which is given by minus y plus xz over z squared plus 1 quantity squared, and then minus yz minus x over the same, and then 1 over z squared plus 1. And they tell me that this is what? Water in a bathtub. Cool. And then they want me to rewrite f in some wackadoo way where I'm supposed to figure out how the water's moving given that I rewrote it this way. Okay? So how do I rewrite it in this wackadoo way? What are they doing? Oh, they're combining like terms. Okay, so they're noticing, check this, there's a over z squared plus 1 squared under both of these guys, right? You guys see that? And then there's like this dude here that's got a z's, and this dude here that's got a z. Right? And then there's also these guys that don't have a z. So they're just saying, hey, let's rewrite this, and we'll do this. So there's a minus y I, that's this part, over z squared plus 1 quantity squared. So that's the, out of the first bit, the bit that doesn't have a z. And then what else is there that doesn't have a z in those first two?
The minus x.
Yeah, there's a minus x is going to be a plus x. And which vector component did that come from?
J.
That came out of the j's. You guys all see that? So that's like this first y and that second x pulled out. And then there's also a plus, let's see. So what about the ones where there is a z?
There's a positive xi and then a negative yj.
So I'm with you that there's a negative yj, but there's a negative xi. You guys see that? Why would you ever want to do this?
Isn't it minus a negative if we look at the problem again?
Oh, did I write one of them down wrong? That would be good, because right now x plus z and a minus yz. No, that's what there is.
I think
Oh,
there's
so
supposed to be.
the k component is minus.
Yeah, and then the k component I dorked up.
So that's it.
And then there's a minus k over z squared plus 1. Okay, and now they want me to describe how the water's actually moving, right? So,
Negative in the j, doesn't it have parentheses over the entire y coordinate? Like that negative is applied to the entire y coordinate, not just the yz?
yeah.
Can we assume that the x and y grows slower than the z because the square is on the denominator?
Oh, because it applies.
It's going to be positive.
What? X and y don't grow at all. They're just coordinates.
I mean like the magnitudes.
Oh, on this guy?
Yeah.
Yeah, so one thing we could notice is that, like, this piece, right, has something fourth order in the bottom. You guys see that? There's a z squared squared. So that's fourth order in the bottom and first order in the top. So as you go away from 0, right, like, but it depends on which way you're going away from 0. You guys see that? So yeah, you could kind of think that way, but you run into problems with like, well, which direction am I headed in? But what I think we can do is I think we can say this. So what does this last dude mean?
That is an inverse square.
You guys see that? Like, all things being equal, regardless of where you are in terms of x and y, this component is negative, right? You guys see that? And it's always negative regardless of what z is to.
So as you go up, you go down faster.
You guys that? Careful. So as you go up, right, what are you increasing as you go up? Z, which is making the bottom of this bigger, which is making this z component smaller. You guys see that? So this dude here is down, right? That's telling us that this water's flowing down. How much of a surprise is that?
It should.
It should, if it's leaving the drain, right? It should be going down. This guy, though, right, also has a slower as you go up.
That makes sense.
Does that make sense? So as you move up in the bathtub, right? So I'm thinking of my points as being in the bathtub. And so when I'm saying down, right, I'm meaning that things are flowing towards the bottom of the bathtub, right? And that the rate at which they're going down gets slower as you go towards the top of the bath.
Which is kind of how that spiraling effect thing occurs.
Yeah, which kind of makes sense, right? Because the drain's on the bottom. So where's it pulling stuff from?
The bottom.
The bottom, right? So it's kind of making a step, right? You guys see that? Like, if you had a drain, right, and there's like water here, like the first water through the drain is going to be the water that's close to the drain.
Yeah.
And then the next water into the drain is going to be this water. But first, this water has to go into that space, right? And there's more of this water than there was of that.
So it'll take longer.
So it will take longer. Okay, see that? Because first it has to fill in. And then the next layer out is going to take even longer because it has to fill in the smaller layer and then the smaller layer onto that. You guys kind of follow that? Okay, what else is going on here? What does that freaking thing look like?
Minus.
Simple.
Oh, yeah, that's the.
That's the spiral thing.
Oh.
That's that classic spiral vector field, right?
You can tell which hemisphere it's in.
So there's definitely some kind of spiral and some kind of things are going down. And then what's this other dude doing?
It's spiral. It's also in the z value, so it's the spiral heading. Oh no, that's a negative x
Bathtub is
negative.
kind of like, right? Slanted?
No. Maybe. So I think there's an easier, this dude here. That's going to be x and y scaled by z, right? Like this guy points in the direction of minus y comma x, right? Which direction is this guy pointing?
Yeah, minus xz minus yz.
Oh, towards us.
Like just for a set z, right? This thing points away from the,
Origin.
well, yeah, so
It's pointing towards something. I just don't know what that thing is. Context.
Point back towards the origin.
so here's a point, right? This guy points along the circle. You guys all with that? Where's that guy point?
Towards the drain.
Yeah, towards the center of the circle, right? That guy points at the drain. So this dude spirals. What's that one do?
Puts it. Yep.
That's spiral in, right? Oh, wow. Sorry, wrong color. Really, it's only in. You guys see that? The spiral is really coming from this. So you've got a spiral, you've got movement in.
Faster downwards.
Yeah, and that in gets closer to 0, right? As you get down to the drain. Because, duh. right? So you've got spiral, in, and go down. That seems like what a drain does.
And the deeper you are in the spiral, the stronger it is.
Yeah, and the deeper you are in the spiral, right, the less in there is because, well, you're already pretty close to the center. You guys see that? Okay, what's part B? So it tells me the drain is blah, blah, blah. A disk in the XY plane with a center at the origin and radius 1 centimeter. Find the water at which, or the rate at which water is leaving the bathtub.
That sounds like a flux.
That sounds a lot like a flux. You guys see that? So part B is going to be the flux of this vector field through that disk that they described.
So this would have units then, you know you're working with water in your bathtub, right?
Yes!
Yep. B actually says give units.
And they even gave me my units. So this is going to be a flux, right? So it's going to be the integral, really a double integral over disk, right, of a vector field dotted with D area, right? You guys all good with that? Okay, so I'm going to assume you can calculate that. What are the units on this thing?
Centimeters.
Cubic meters per second.
So they told me what? Did they give me units? Yeah, they tell me the velocity vector in the drain is in centimeters given by this stuff, right?
Cubic centimeters per.
So this is going to be cubic centimeters per
Second.
time, right? What did they say time was?
They said centimeters per second, so it should be the second.
Yeah, centimeters per second. So this is cubic centimeters per second. Otherwise known as milliliters per second. Cool? All right, part C. Find the divergence of F. So what do I expect the divergence of this vector field to be?
Divergence is gradient dotted with F.
Yeah, so we take the gradient, we dot with F, right? Or the idea of the gradient at least, and dot with F.
Let's see, it's so. Okay, so I see is
What do I expect this to be?
Pretty intense spiraling towards.
Well, it's water.
It's water.
Oh, right, so it can't be,
I suspect that this should be 0,
yeah, because it can't be.
right? Because water doesn't tend to get compressed. So if this vector field does in fact describe water, right? Probably this guy's 0. You see it? It takes a weird scenario for water to have a positive or negative divergence. I'm expecting that divergence to be 0. What's that saying? Well, that's me thinking about these little guys again, right? Like, if the divergence was positive somewhere, that would mean that, like, there's water appearing out of nowhere. Right? Or, like, the water is getting less dense somewhere. But water doesn't really tend to do that.
If it's freezing, it does. If
Yeah.
it's freezing, it gets bigger and less dense, so.
Yeah, water's weird.
but
Do you guys know that about water? That's really bizarre.
Yeah, that's the one thing that gets larger as it freezes.
There's,
One of the few things.
yeah, there are like 3, but.
Okay.
Okay, so I'm going to assume that I'm out of time and you can calculate the rest of these.
Okay. So